Friends, welcome to VK lectures. In this lecture we are discussing the quantum mechanics part, which is the perturbation theory. As we have seen, we are just once again writing the first order correction to the energy. First order correction to energy, that is En of 1 is equal to psi n h dash psi n. Now this is, we can write it in integral form, psi n star h dash psi n dx. Now this limits, what are the limits? Limits are where the perturbation exists. Perturbation exists. Or simply you can write limits of h dash. Limits of h dash. Now for a constant perturbation, now let's write here the first one, that is constant perturbation. Constant perturbation, let us take an example, h dash equal to some b. Now then the first order correction En of 1 is equal to, let us write down here, this is En h dash b, sorry, h dash n, this is equal to n b en, because we know that h dash is equal to b. Now since b is constant, because this is a constant perturbation, we can write this equal to b into n. Now this n is nothing but 1, because this is n is nothing but integral psi n star psi n dx. This is nothing but the total probability equal to 1. And since b dash has limits, we can say the En dash or En of 1 is equal to constant into probability. Because psi n star psi n dx is nothing but probability. Instead of writing 1, we can write p as probability, because the maximum value of probability is 1. Since the limits of perturbation is the limits of h dash instead of the entire limit, it is better to go with the probability. So we can write the constant of for a constant perturbation, the first order correction to energy is given by that particular constant into probability. Let us take the case of a one-dimensional box, 1D box. Okay. A constant perturbation of V naught is applied to the Hamiltonian of one-dimensional box. in 0 to L. So the one dimensional box is 0 to L, and V naught is also applied from 0 to L. So if V naught is applied from 0 to L, we have to consider the probability from 0 to L itself. Okay, so sorry, we will put 0 to L by 2. Okay, 1D box is from length 0 to L, and the constant perturbation is applied from 0 to L by 2. Now we know the energy, first order correction to energy, is given by the constant perturbation into the probability. So now the question is, what is the probability of finding the particle from 0 to L by 2? So this is the one dimensional box, and here you have the wave function 0 to L, and this is L by 2. So the probability of finding the particle from 0 to L by 2 is 1 by 2, and from L by 2 to L, this is also 1 by 2. Now what is the probability of finding the particle from 0 to, this is L by 4, this is L by 2, this is 3L by 4, and this is 0, and this is 1. Sorry, this is L. Okay, in this all region we have already found, we look into that, but the question is from 0 to L by 2. So from 0 to L by 2, the probability is 1 by 2. So En of 1, first order correction to nth state energy, is 1 by 2 the constant into probability. So what is constant? Constant is V naught into probability is 1 by 2, so that's equal to V naught by 2. So this is the first order correction to the energy. Then the total energy will be equal to En naught plus first order correction. So what is En naught? En naught is En square pi square h cross square by 2m L square plus En dot 1, that is V naught by 2. So the total energy will be equal to this much. Okay, so where V naught by 2 is the first order correction, this is the zeroth order correction, or the unperturbed energy. Probability is given by the formula as we have discussed earlier. It is P is equal to integral from x1 to x2. This is where the point where we have to find the probability, psi star psi dx. Now here we have the 1D box which is in ground state, which means n equal to 1. Then for a 1D box, now this is one more parameter we have to define here. It is unsymmetric box. It is unsymmetric means it is from 0 to L. The length of the box is from 0 to L. So from 0 to L, if you consider the probabilities in each of the following session, that means from 0 to L by 4, the probability is 1 by 4 minus 1 by 2 pi. From probability from L by 4 to L by 2, it is from 1 by 4 to 1 by 4 plus 1 by 2 pi. From L by 2 to 3L by 4, it is 1 by 4 plus 1 by 2 pi. And from 3L by 4 to L is 1 by 4 minus 1 by
1 by 4 minus 1 by 2 pi. Now if you consider the probability from uh, uh, 0 to L by 2, you have to add these two probability from 0 to L by 4 plus probability from L by 4 to L by 2. So if you add both, what you are going to get is 1 by 2 pi will go, so you can get 1 by 4 plus 1 by 4, that is 1 divided by 2. Now you can also get questions like probability from 0 to L by 4 and probability from sum of the probability from 0 to L by 4 and 0 to 3 by 4 L to L. That means in this range, in this region as well as in this region, that means the first and the fourth region, what is the probability? So first and fourth region, the probability is 1 by 4 minus 1 by 2 pi plus 1 by 4 minus 1 by 2 pi. So that will be equal to 1 by 2 minus 1 by pi. So this is how you can get to the probability. In if at all there is some other parameters, that means whatever is not given here, you can use the limits. If something is asked 3L by 8 to 7L by 8, this is a possible question, psi star psi dx. So you have to integrate and substitute the limits, which will give you the probability from 3L by 8 to 3L by 8 to 7L by 8. So this is how you can get probabilities.
The other kind of the perturbation is h dash is equal to b times x, some constant into x or some constant into x square. So this is perturbation depending on the position. Okay, so here we have position x, this is x square. So our aim is to find the first order correction to the energy En of 1. So we can write this as n h dash n, so that's equal to n h dash, we can write it as bx times n. Now similarly we can take this out, b which is constant, so it will be n x n. This is nothing but the expectation of x, so b times expectation of x as the first order correction to the energy. Similarly, if it is h dash is equal to bx squared, then En, first order correction to energy, is given by n bx squared n. So that's fine. We will get b which is constant, n x square n. Now that's equal to b into expectation of x square. So this is another value, and please remember that the expectation is within the limits of h dash. Even here we have the limits of h. that is perturbation. So, what we know is we if the perturbation h dash is of the form bx or bx square, uh, we have to take the expectation of the x square and the expectation of expectation of x and x square times the constant b. So for h dash, uh, if it is the perturbation is bx, then we have different models. Some models are one dimensional box, 1D box from 0 to L by 2, 0 to L. Then another 1D box from minus L by 2 to L by 2. The first one is unsymmetric box. This is symmetric box, symmetric with respect to 0. Wave function will also be symmetric. Then we have linear harmonic oscillator and hydrogen atom. These are the basic models that we know. Now we need to find out expectation of the x, expectation of x square. These two are generally we need. Sometimes x cube and x power 4 for not for all but for some may be asked. So 1D box expectation of x is L by 2. Expectation of x square is L square by 3 minus L square by 2n square pi square. I request you to remember and by heart these values, or else you must be able to derive this at the time of the exam. So that is 1D box. Then 1D box symmetric. So for symmetric box, expectation x is 0 and the expectation x square is L square by 12 minus L square divided by 2n square pi square. Remember, it is changed to 12. For linear harmonic oscillator, since it is symmetric, it is of this form. This is the linear harmonic oscillator wave function. So it is at from 0 it is okay. Now if it is not at the center, if the center of the linear harmonic oscillator is not at the center, for example it is at x equal to a, then expectation x is a. Okay, so then we have x square expectation h cross square by h cross divided by 2m omega into 2n plus 1, where n is equal to 0, 1, 2. It is the state, first state, second state, third state, etc. First state is nothing but ground state. This is the first excited state, second excited state. So h cross by 2m omega into 2n plus 1, and x cube, it is again 0, and for x to the power 4 it is h cross by 2m omega to the power 2 into 6n square plus 6n plus 3. So this is another formula. Then for hydrogen atom, we have radius instead of x. So I will write expectation value of r is equal to 3 by 2 a naught. Expectation of r is 3 by 2 a naught. Expectation 1 by r is 1 by a naught. expectation r square is 3a0 squared, then expectation of 1 by r square is 2 by a0 square. So these are the expectation values. Here the next session is finding out the first order correction to the wave function. First order correction to wave function. Wave function psi. Now this is represented by psi for the nth state, the first order correction, equal to sum of m not equal to n psi m h dash psi n into psi m divided by E n naught minus E m naught. So this is the first order correction to the wave function. This also we can write it as sum over m not equal to n m h dash n by en naught minus em naught into m. So now let us see the second order correction to energy. For formula for the second order correction to energy. We have seen the first order correction to energy, which was written by, which can be written as En of 1. Now we have the second order correction, which is given by En of 2. That's equal to sum m not equal to n, the magnitude of m h dash n whole squared divided by En naught minus Em naught. So this is the second order correction to energy. M and N are the different states. En naught is the energy of the unperturbed energy in the nth state. This is the unperturbed energy in the mth state. Okay. So with the final few notes we can wind up the perturbation. So the first one, that is first order correction to energy. First order correction to energy depends on sign of the perturbed Hamiltonian. Depends on sign of the perturbed Hamiltonian. Now the second one is spacing between the energy levels. Spacing between energy levels remains same. This is important. Remains the same before and after perturbation. Before and after perturbation. Now here is a clause. This you have to remember that the perturbation should not depend on n. N is the order. If it depends on n, the energy levels may vary. But if as long as it doesn't depend on the order, state of the state, that means the in which state our system is in, then it does not depend on the state. Perturbation as matrices. Here you can get many questions. Perturbation as matrix. Okay. Now we know for any quantum system we can represent the perturbed Hamiltonian H dash is equal to H naught, that unperturbed system, plus the Hamiltonian which is added, and this added perturbation can be first order plus the second order plus the third order, etc. Okay, according to how many corrections that we need to take, how much order of the correction that we need to have, we can take. If we need first order correction, you need to find out H1. If you need the second order correction also, you need to likewise. So now we are going to write the H dash, which is the if it is in the form of matrix, then you can also write the H naught in the form of matrix. That means the unperturbed Hamiltonian plus the perturbation what is added in the form of matrix. Now just as an example, you can take A plus lambda 1, which is one perturbation, E or epsilon minus epsilon, then B plus lambda 2. Okay, so this is the perturbed Hamiltonian, now which can be written as in the form of H naught, which is unperturbed Hamiltonian, that can be A 0 0 A, sorry, it is B. Okay, and what about the perturbation? Perturbation is whatever is left, lambda 1 E minus E and lambda 2. So this is how we can write the perturbation or the as matrix. How can we represent the perturbed Hamiltonian H dash? Usually what is given is H naught, which is this is H naught, this is H dash. Usually H naught will be diagonal matrix. Diagonal. It need not be always diagonal, but generally it is diagonal. Now, but if you can make it diagonal, that is better. Now, now if it is diagonal, the A and B, for example, in this case, A and B are unperturbed energies, corresponding to two states. If since it is a 2 by 2 matrix, we will have two states for this matrix, that is psi 1 and psi 2, and corresponding to psi 1, A is the energy, psi 2, B is the energy. So what are A and B? A and B are unperturbed energies. Unperturbed energy. And states corresponds to psi 1 equal to A0. So it is, can represent it by 1 0, and psi 2 by 0 1. Now where does that A and B go? A and B goes for can get cancelled when normalizing. Okay, so psi 1 is 1 0 and psi 2 is 0 1. So this is the eigenstate. Eigenstate. A and B are the eigen values for that particular diagonal perturbed Hamiltonian. Okay. Coming to the first order correction to energy. So first order correction to energy, that is En of 1. Okay, so first order correction to energy. Now we know H dash, we have to take it from the first order Hamiltonian correction, that is lambda 1 E minus E and lambda 2. So this is the perturbation, and what is first order correction to energy? En dash, let us write En dash is equal to En H dash En. Now that is suppose if it is E1 of 1, which means first order correction to the energy of the first state is equal to 1 H dash 1. That means the first state, the Hamiltonian, and the first state. That means 1 1 of H dash. What is 1 1 of H dash? 1 1 of H dash is equal to 1 1 means what is the 1 comma 1? First row, first column of H dash, that is equal to lambda 1. Now this also you can get it from 1 is the vector, that is 1 comma 0. This is psi. This is psi 1 H dash psi 1. First one psi 1 is in as a row vector because it is a bra vector. Then H dash, what is H dash? Lambda 1 E minus E lambda 1. And what is again psi 1? Psi 1 is 1 0. Now this multiplication would yield first you have to, this is 2 by 2 matrix, this is number of rows in the column. Rows is 1, column is 2. This is one column, rows is 2, column is 1. So multiply these two vectors, that is this and this, and then multiply by 1 0, and what you will arrive at lambda 1. So lambda 1 is the first order correction to the first state. So similarly, first order correction of to energy of second state will be equal to 2 comma 2. What is 2 comma 2? That is lambda 2. Here you write lambda 2. So lambda 2. So now what conclusion that we can make? The first order correction to energy values are the diagonal elements in this case 1 comma 1 and 2 comma 2. What are diagonal elements here? Lambda 1 and lambda 2. So diagonal elements of what? Of h dash. What is h dash? Perturbation added. Okay, first order of h dash when, this is important, when h naught is diagonal. This is applicable only when h naught is of the form a, b, c, etc. All other elements should be 0. If h naught is something like this, which is diagonal, then first order correction to the energy will be 1, 2. That means diagonal elements. Okay. Now we have the second order correction to energy. Second order correction to energy. So how we can represent En of 2 or En2? That is equal to sum over m not equal to n. As long as m not equal to n, then m h dash n, which means m comma n, the element m comma n in h dash squared divided by En naught minus Em naught. For example, let us take the same case here. H dash is equal to lambda 1 E minus E lambda 2. So this is the perturbation. Now we need to find En. Let us find E1, second order correction to the first state. That's equal to sum over m not equal to n means when n equal to 1, n value is 1, so m value should be equal to 2. So m2 h dash n is 1 squared divided by e1 naught minus e2 naught. Now what is e1 naught? E1 naught is the eigenvalue corresponding to unperturbed Hamiltonian. Eigenvalue corresponding to unperturbed Hamiltonian, that is A00B. So E1 naught equal to A, E2 naught equal to B. These are the eigenvalues. Eigenvalues are nothing but energies, unperturbed energy. So let us write the, so that's it. There is no need of sum because there is only one term. So 2 comma 1 from this Hamiltonian is second row, that is minus e. So minus e squared divided by e1 naught is a minus b. So that's equal to e square by a minus b. Now what about e2 of 2, which means the second order correction to second state. So sum where n equal to 2, m equal to 1, m as 1, h dash 2 divided by e2 naught minus e1 naught. This one squared. So e squared divided by e2 naught is b minus a, that's equal to e squared divided by b minus a. So that is it for the second order correction to energy. Next is first order correction to wave function. First order correction to wave function. So psi naught is the unperturbed wave function. Then first order correction would be psi 1, which represent the first order correction. If you write 1, it represents the first order correction to the first state, and this is first order correction to second state. Okay. Or in general we write psi n of 1, which says first order correction to nth state. So psi n of 1, that is the first order correction to any nth state, is equal to sum over m not equal to n, m h dash n, then en minus em, yes, how it is, em naught and em naught. Then you need to write the state, on which state you are talking to. So if you represent n, the next state will be m. Okay. Now with respect to the question that we have, our h dash is equal to lambda 1 e minus e lambda 2, then psi naught or psi 1 naught is equal to 1 0, and psi 2 naught is equal to 0 1, This is all what we have, and En naught or E2 naught, E1 naught is equal to A, E2 naught equal to B. This is what right now we have with us. So if I want to find psi 1 first order correction to uh, first state is equal to I have to start with second 2 h dash 1, then it should act on the second state. It should act on as long as it is not equal to 1. If there is another state 3, I have to add 3 also. Then E1 naught minus E2 naught. This gives us 2h dash 1 is second row, first column, so it is minus E, so minus E divided by this is E1 naught is A minus B into second state. What is the second state says? Second state is 0 1. So this is a constant value, multiply this constant value with 1, that is the answer. So what will be that? First term is 0 minus E divided by A minus B. Now you can also find psi 2 of 1 first order correction to the second state, that is 1 h dash 2, then again 1 will come divided by E1, so E2 naught minus E1 naught, that's equal to 1 h dash 2 1 h dash 2. So first row, second column, that is E divided by this is B minus A into first state 1 0. First state is 1 0. So that will become E divided by B minus A 0. So this is the first order correction to the first state. First state, that is the wave function. So that's it. As a practice work, one can try solving this question. H naught is given as E naught 0 0 E naught minus E naught. H dash is given as lambda times alpha mu beta. So this is unperturbed. This is the perturbation. The Hamiltonian H dash Hamiltonian H will be equal to H naught plus H dash. That is it. Okay, so since it is a 2 by 2 matrix, you will have two eigen functions, psi 1 psi 2. Corresponding to psi 1, you will have ground state energy, that is first state energy, that is E naught, and E1 naught and E2 naught. This is the energy, that is the corresponding to the particular state. Now based on that you will also have E1 first order correction to the first state and first order correction to second state. Then find second order correction to first state as well as second order correction to second state. Then first order correction to wave function first state and the second state first order correction. All this you can find out from the given matrix. Okay, thank you for watching.